Okay folks, part 2 for this evening. We will go through a couple of examples. Then I'll give you about a day, like let's say Wednesday-ish, to work through some of this homework. And then, Thursday I'll come back at you with another lecture on electric fields, okay? Just so we keep moving forward. We'll be grateful that we're not losing so much time now come April when we have the extra time to review. And we're doing okay time-wise. We are losing a lot of days here, but, it's conditioned. The light just turned yellow. We're nowhere near, like red alert yet. Right? We've still got another month of winter. What the heck, right? All right. Let's do some examples. First, we did part ways with a little bit of Coulomb in class today. I did show you that FET sim and asked you to draw a graph of your data. So, just make sure you do that. And I will look at that in the lab book at some point, but we got to get back together and talk about that. Just a quick little graph, okay? I'm not going to write out the units again. This is Coulomb's law. You will find the K constant. Excuse me, I just kind of burped a little bit there. It's after dinner. I usually don't teach now. Newton meters squared per Coulomb squared. I wrote that down. That is on the equation sheet. And, so there you have it. Okay? This is what we're going to do examples on. So, let's do the quick yawner. 4 microcoulombs amp of positive and 2 microcoulombs of negative. Remember, we usually deal with small teeny bits of charge, okay? Notice how I've accounted for the positive and negative there. Sometimes it'll be given as a negative. I don't use that in my math. I use the 4 and 2, and I understand that it's attractive because opposites attract. Paula Abdul sang a song about that in the 1980s. Go find it on Spotify. It's a good one. Opposites attract. All right. Let's figure out the magnitude of the force. F is K, Q1, Q2, R squared. Oops. Let me just make a nice 0.1 meters. Okay, because I don't have a calculator handy. I want to do this in my head. All right. So here we go. 9 by 10 to the 9. Let me get, come on, it's after dinner, okay? I'm off the clock, so I'm going to skip the units, all right? Micro is secret code for -6. It's on the equation sheet if you don't know it. 10 to the -6 and a 0.1 squared. All right, so here's the easy way to do this. 9 times 4 times 2 is 72. 9 by 4 is 36. Double that is 72. Now, I have to account for units. 9 take away 12. My math tells me that's 10 to the -3. Okay? And I have 1/100th in the denominator. So I have 1/100th. So by my math, this ends up being 72 times 10 to the -1 newtons. By the way, all these units do clean up to be a newton. All of these units do clean up to be a newton. I guess I should have done it at least once for you. By the way, that's 7.2 newtons. Okay? It's definitely a noticeable force. Imagine what that's like on a spring scale. That's some force. Newton meters squared, Coulomb squared. Coulomb, and I did all my conversions. This is in coulombs because I converted. Divided by meters, and you're squaring that, and you see all that's left is a newton. So I wasn't kidding you. All right. So that I didn't need to show you, but I'm going to show you some tricks. Okay? You will see some problems where it's like this. You'll have a charge and a charge, and then maybe double the distance away you'll have a charge. Okay? And you might have Q1, Q2, Q3. Alright, you would do this math up here. Let's say it was 4 and negative 2 separated by 1. It was the same deal. And so you would see that it's 7.2 newtons of attractive force, because you would do all that math. Okay? Now, let's say, okay, I've got it reversed, but we'll just stick with it. Let's say this was also 4. So wait, this 4 tugs on the 2. This 4, from a charge standpoint, would tug on the 2 the same amount, except that it's double the distance. So the influence here would be not a little smaller, not half as much, because this distance is double this distance, but rather it would be only a quarter as much, because when you double the distance in the denominator, your new answer is a quarter. So this would be 7.2 over 4 is 1.8 newtons. That's half of a half. Half of this is 3/6. Half of that's 1/8. Okay? So sometimes you get the question, what is the net force acting on 2? And you would say, doggone it, they're going to make me do like math here, Q1 tugging on 2 and Q3 tugging on 2 and do all that stuff. No, be smart. Do it once and then understand that it's the same charge, twice the distance. Okay? If it were 4 times the charge, so 16 microcoulombs as opposed to 4 microcoulombs, alright? This one's going to pull. This one will pull quadruple as much, but the fact that it's twice the distance knocks it down to a quarter. So what you end up with when you go Q1, Q2 over R squared, you end up with this charge stayed the same. The second charge is now quadruple. And doubling the distance, you get 4 over 4, or unchanged, which would make that 7.2. We exist in a 3-dimensional world, at least 3 spatial dimensions and a time dimension, and we can argue some of the higher ones, but that's not the scope of this course. So here's the last thing, and wow, we're going to get this one done in less than 10 also. Charge here, charge here, charge here. Find the net force on this one. Let's call it 1, 2, and 3. F net on 2 equals what? You're like, oh, dang, man, vector addition. So yes, you are going to have to do the mathematics here. Let's say these are all the same charge. Q, Q, Q. I don't know the numbers. And it's an equilateral triangle, so all the distances are the same. Do the math here. If this charge is of equal size to that charge, then you are going to get an identical length force vector, and now you can do your symmetry. There's a bunch of ways. If I just want to do a vector addition, remember, we got to go tip to tail, folks. So this is what 1 does to 2, and then you come in here, and oh, it's not a right angle, sorry. And then what that one does to 2, and you'd see that the net force is going to point vertical. Okay? And you'd have to do all your just nasty, nasty components. The x component of that one, the y component of that one, the y component of that one, the x component of that one. And then you add up the y's and add up the x's. Wait! I don't need to do the math for the x's because this left cancels this right. Now all of a sudden I'm starting to use my symmetry. And I'm going to say boom to that, okay? So really, again, all you have to do is calculate the length of this vector, KQQ over R squared, okay? And then, yes, you are going to have to resolve it. This is 30, so that's 60. So you figure out the y component here, and the answer will be double that y component in the downward direction. So the well-written problem is the problem that enables you to see some of that stuff, okay? those are the tricks. You really can nail problem set 2. So see if you can dig deep. I know it's, cold days and all that good stuff. See if you can dig deep and work on it, okay? I think it's definitely possible. Peace.